Welcome to the second mini lecture on Introduction to Artificial Intelligence and Machine Learning. We're going to discuss some basic concepts. We already went through the history of artificial intelligence, the relations of artificial intelligence to machine learning, and the machine learning life cycle. Today we're going to focus on basic concepts. One of these basic concepts is we need the machine learning to use data to learn, and for that we normally build some data sets or collect some data sets. What is a data set? A data set is a structured collection of data that is used in machine learning to train, validate, and test the models. It serves as the foundational input for algorithms to learn the patterns, the relationships, and make the predictions. And there are several characteristics that we want them to achieve. One of it is that it's relevant. That means that the data set we collect match the task or the problem that is being solved. That it has a diversity, that meaning that it will cover a wide range of examples to ensure generalization. It will be of high quality, free of noise, errors, and inconsistencies, and also large enough to represent the problem domain effectively. In terms of the different components of the data sets, this is an example of a tabular data set that is a subset of measurements on data from the Wisconsin breast cancer data set. You have the link in the page. Each row in this table is what we call an observation or instance. It's basically the individual record or row in the data set, and in this case is data from a patient, for the different patients. The different columns in this case, except for the last one, which is the diagnosis, are called features or inputs. These are the attributes or variables describing the data points. For example, this is a supervised learning to classify tumors, breast tumors into benign or malignant. So there's a number of measurements. I only put 3 things here, but there are many more in the original data set. And each of these columns we call feature. The label or class is the diagnosis in this case. And this is what this is the target variable, or what we call ground truth, used in supervised learning. It represents the value the model aims to predict. Last thing, I'm going to point out to metadata. Although this is not necessary in the particular file of where the data set is integral part of the data set. This is an additional file which contains information about the data set. And you can, for example, it could contain the headers. This could be in a separate file explaining what each column is. It could also contain the data types and descriptions and numbers of positive or negative, in this case, benign or malignant cases. I mentioned before that for supervised learning, we use label data. But what is a label? A label is an annotation to the data. One data item may have multiple labels. For example, if you're trying to do secondary structure prediction, we could indicate that an amino acid, this is a sequence, and let's say we're focusing on this amino acid called alanine. We could label it as being in an alpha helix, but we could also label it as being part of a transmembrane domain. So in this case, we have 2 labels. And that's we call labels because these sets of values are not mutually exclusive. On the other hand, we have classes which are defined for classification purposes. Classes are mutually exclusive. We have the same residue in the protein could only be part, either the one at that particular position could only be part either of alpha helix or a beta strand or a coil, which is another class of a secondary structure Another example in that regard could be if you have publications that you are trying to classify as relevant or non-relevant for a particular topic of interest. It cannot be both things at the same time. If you remember, the machine learning algorithms understand numbers, so we need in some way to convert the classes and labels into some kind of numeric representation. And encoding is the methods that is usually used to represent the categorical data into numbers. In this case, each class, each secondary structure class is represented by a unique vector where you assign 1 for the particular structure and 0 for the others. Models often require training data set, which involves basically using this data set will help automatically adjust the parameters of the model and improve its performance. The training data set could be divided into training and validation. So a part of it will be used to validate the system, and in this case it won't influence the training. So we can use the validation to check, for example, for potential overfitting. You're going to learn about it in a moment. Once the data model is trained, so we finish with this part, then the testing comes in. So the testing, the part of a data set that is part of the testing, we call it evaluation data set, has never been seen during training. This is called the holdout set. In addition to the approach of doing this training validation, another approach is called cross-validation. In this case, the dataset for training the model is split into k evenly fractions, and this will form different training sets and validation sets, and the performance is compared across each partition to select the best hyperparameters. Then we have the concept of loss or cost functions. These are the mathematical functions that measure the amount of disagreement between the obtained and ideal outputs in machine learning. Loss in machine learning measures the discrepancy between the predictive value and the actual value for a single instance. It provides a way to quantify how well or poorly the model predictions aligns with the target. So, the term loss of function and cost function are often used interchangeably, but they have subtle distinctions. Loss function refers to the error calculated for an individual training example, whereas the cost function represents the average of the loss function across all training data, providing an overall measure of the model's performance. These functions are fundamental to supervised learning algorithms that rely on optimization techniques. We have here an example of mean square error loss for regression problem and binary cross entropy loss for classification problems. Another concepts that I want to introduce has to do with parameters and hyperparameters, and I kind of mentioned this in a couple slides before while talking about cross-validation. To be able to learn on training data, models contain adjustable parameters whose value can be changed over the training process to achieve the best performance of the model. These are called parameters. We have examples here. We have our model that is being trained, and these are the things that are adjusted in order for the model to fit the data. These parameters are the ones embodying learning. This includes coefficients or weights of linear and logistic regression models, biases, and activation function in neural networks. These are just a few examples. On the other hand, the process of training a model involves choosing the optimal hyperparameters. Hyperparameters are parameters whose value control the learning process and determine the values of model parameters that a learning algorithm ends up learning. So it's everything that shapes the training. We said before training, these are things like learning rate, batch size, numbers of lanes in a neural network. Basically, anything in machine learning and deep learning that you desire their value or choose their configuration before training, those are called hyperparameters. These are called to be external to the learning. Another concept we are going to introduce is inductive bias, and this is the assumptions that the model makes about the underlying structure of the data to generalize better from limited observations. So this is what inductive reasoning involves, forming generalizations from specific observations. But a single observation can theoretically support an infinite number of hypotheses. In machine learning, we work with a subset of observation, that means sample, to develop models that generalize to unseen data. And the goal is to derive a general rule that applies to the entire population based on limited data. Each machine learning model represents a hypothesis defined by the algorithm and its parameters. While multiple models can explain the training data, their performance on unseen data may vary significantly. So inductive bias refers to the presence of or constraints a model imposed on the hypothesis space. By prioritizing certain hypotheses, the model makes assumptions about the underlying data. For example, given two data points, many functions could fit them. The choice of function reflects an inductive bias, influencing how well the model performs on new data. Here is an example of choosing recurrent neural network models are specifically designed for sequential data. So in a way, when you use this algorithm, you're making the assumption that your data will have a sequential and dependencies. And this is okay when you're using DNA sequence, for example, for predicting DNA binding sites of transcription factors. So, because we are leveraging this assumption of sequential dependencies in the data. Following with the generalization in machine learning, ideally we want that the machine learning models perform well with unseen new data. That is, that they can generalize. Underfitting and overfitting are major causes of poor model performance. Underfitting, which is, a good fit, let's start with that. A good fit means that our model, which is the dotted line here, the new data and the new model are a good fit. On the left side, we have what we call underfitting, meaning that the model is failing to learn the underlying relationship between the variables. Here we have, this is our model and these are our data points. It can occur with inadequate data or when we use a simple model on a complex problem. On the other hand, we have the issue of overfitting. Overfitting, it means that the model learned the noise in the training data. This can be caused by using a model with too many parameters or by continuing training after it has learned the true relationship between the variables. So these two are connected to the bias and variance. Bias occurs when a model prediction consistently deviates in a particular direction, reflecting a systematic error. It is a difference between the model expected prediction and the true value we aim to predict. A model with high bias imposes a strong constraint, limiting its ability to adapt to complex patterns in the data. For instance, fitting a linear regression to data with a nonlinear pattern will result in poor performance regardless of the amount of data collected. The model simply cannot capture the curves in the data. If you remember the example we saw before, it could be an issue of underfit. A model for 2 points, it will fit okay, but if I show new data and this data is a curve, then it won't never, disregarding how many more points we add to the data, it will never fit well. So models with high bias make stronger assumptions, usually are simple models and have reduced flexibility. Those with low bias have fewer assumptions, more flexibility to model diverse function, but potentially higher risk of overfitting. Variance, which is here at the low part of this table, refers to how much a model's predictions change when it's trained on different subsets of the same dataset. It measures the model's sensitivity to small fluctuations in training data. High variance indicates the model is too flexible and overly dependent on the training data, capturing noise along with the signal. This leads to poor generalizations to unseen data. Low variance, on the other hand, means the model is less sensitive to specific details of the training data. Let's look at the example on the right. So now imagine the dartboard on the right here. We have two scenarios. In this case, each dart represents a trained model trained on a different dataset. The variance is the spread of the darts in the dartboard around the target. In a high bias scenario and low variance, the darts cluster far from the target center but consistently missing the target. Models are consistent but inaccurate. A high variance and low bias model, on the other hand, has darts scattered widely across the board, missing the target inconsistently, but models are accurate on average but inconsistent. So controlling the bias-variance trade-off is key to avoiding overfitting and underfitting. So you can see the variance of a model describe, as we said before, how much the trained model changes in response to training on different training datasets. In general, we like models, the ones on the lower left here, which have low bias and low variance. And here we see the relation between the bias and the variance and the optimal and underfitting and overfitting. And this is we are graphing the model complexity and the prediction error. So the optimal would be somewhere in the middle here, where we have an intersection of bias and variance curve. So these are the concepts, the reference for the information in the slides. Hopefully you have now some better basic knowledge of concepts that we are going to use throughout this workshop. Thank you.